All right, the last thing that we're going to look at before Christmas break here is medians and altitudes. This is section 5.3. Okay, so far what we've looked at is we've had triangles. Hold on, let me get my pen here. We've had triangles that we're dealing with, and we have looked at what a perpendicular bisector looks like and what an angle bisector looks like. And you need to be able to recognize the difference between the two. If I'm talking about a perpendicular bisector, that is something that bisects a side. So a perpendicular bisector might be designated like this, and you know it's perpendicular because you're going to see a right angle there. If you don't see a right angle there, we don't know it's perpendicular. So you're going to see a right angle listed for a perpendicular bisector. You're also going to see tick marks. So to designate that this has bisected this bottom side of the triangle, I have to put tick marks here to show you that it's congruent on both sides. So when you're trying to pick out perpendicular bisectors, you're looking for a perpendicular symbol, a right angle symbol, and you're looking for the fact that the side has been bisected or cut in half. When you're looking for an angle bisectors come from the angles, so you're going to have something like that, and you're going to see arc marks. Okay, we have arc marks to show that the angle has been cut in half. That would be something that I would be able to recognize, well, that must be an angle bisector because the line is coming through the angle of the triangle, and I've got the same value of the angle on both sides. So make sure that you can look at that drawing and you can determine which one's a perpendicular bisector and which one is an angle bisector. Okay, now we're going to talk about medians and altitudes. Okay, an altitude is a segment with an endpoint at a vertex of a triangle perpendicular to the opposite side. Okay, so it's going to start in one vertex of a triangle, and it's going to drop straight down, and it's going to create that 90-degree angle. An altitude is perpendicular. What makes it different from a perpendicular bisector is the fact that it's not cutting this opposite side in half. You don't see tick marks on both sides. Those, obviously, it didn't cut the segment in half. It's just perpendicular. Okay, and it's the height of the triangle. So we need an altitude when we find area of triangle, because the area of a triangle is 1/2 base times height. That altitude represents the height of the triangle. So we do need to use altitudes at different times. Okay, it says the three altitudes of a triangle meet, again, just like the perpendicular bisectors met at the circumcenter and the angle bisectors met at the incenter. The three altitudes of a triangle meet at a single point of concurrency. This is called the orthocenter. That's where the three altitudes are going to meet. So if I take this vertex of the triangle and I drop an altitude to the opposite side, okay, an altitude is going to be perpendicular. And if I go to this vertex of the triangle and I drop an altitude to the opposite side, okay, and an altitude is going to be perpendicular. And if I go to the third vertex of the triangle and I do an altitude to the opposite side, they're all going to meet at a point of concurrency. And that point of concurrency is called the orthocenter. Okay? We do not use the orthocenter for much of anything. We typically are focused on the circumcenter and the incenter. The orthocenter, we know what it is, we can define it, but not sure it's used a whole lot. Okay, a couple of things about in a right triangle, it says. This is good to know. In a right triangle, if I'm going to drop an altitude from this, let's say this top point, this top vertex, that altitude actually, if it's a right triangle, ends up being the outside of the triangle. That's actually one side of the triangle is the altitude. And if I go to this vertex of a right triangle and I drop an altitude to the opposite side, okay, because that's where the right angle is, these two legs of the triangle, they're not congruent, but those two legs of that triangle are the altitudes themselves. And then the hypotenuse would have its own altitude here. So the orthocenter would be down here in the corner where the right angle is. Okay, that's all that's saying to you. And then over here it says, in an obtuse triangle, two of the altitudes fall outside of the triangle. Now this is not a picture that's depicting what's happening here, because this is not an obtuse triangle. What they're saying is if I had an obtuse triangle, like maybe like this is an obtuse triangle, what happens is that I have to extend this side in order to drop an altitude from this vertex up here. My altitude would drop here. And I have to extend the side in order to drop the altitude. So the orthocenter is going to end up being outside of the triangle. That's all that's saying. And you'll see some pictures and some diagrams where you see that altitude is actually falling outside of the triangle. Okay, so that's an altitude. An altitude comes down, it's perpendicular to the opposite side, but it does not cut the side in half. Okay, and then we have a median. Okay, you might think of a median as you're driving down the road. The median is in the middle of the road, correct? So a median is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So I'm going to pick a vertex on the triangle. I'm going to draw a line to the middle of the opposite side. This is the middle right here because I have a tick mark on both sides. It's cut that side in half. Again, very similar to the perpendicular bisector. It is bisecting the opposite side, but the difference is that the median is not perpendicular. This angle is not 90 degrees. The three medians of the triangle meet at a single point of concurrency called the centroid. Okay, the centroid. So if I take and I start at this vertex of the triangle and I drop a median, draw the median through so that these two pieces of the triangle, I'm going to the middle of that side, which means that would be cut in half, so they're the same. If I go to this vertex of the triangle and I draw a median to the opposite side, that means I've cut this side in half, so I've got 3 tick marks here to show that these are going to be the same on both sides. And if I go to the final vertex and I draw a median to the opposite side, I've cut that side in half. So you can tell from that drawing that those have to be medians because I don't see any boxes. There's no perpendicular. There's no 90 degrees. But yet I have gone to the middle of the opposite side. So that's a median. And so this point of concurrency in the middle here, where they're all meeting in the middle, has to be called the centroid. Okay, now, some information about the centroid, which is interesting. It says the centroid sits at a point 2/3 of the distance from the vertex to the opposite side of each median. So if this distance right here is the centroid, what it's saying is that this distance from Q to J is 2/3 of the whole distance. And this from Q to N is 1/3 of the distance. Okay, so it says if J to Q is 18, so from Q to J is 18 units, then from Q to N would have to be 9 units. Because the whole thing then, 18 plus 9, the whole thing is 27 units. And if I were to cut that into thirds, I would get 9. So the smaller portion is 1/3, that's 9. And the larger, the longer portion is 2/3, so we double that, we would get 18. It says if the distance from M to Q, so this distance is 7, then the distance from Q to L would have to be twice that. That would have to be 14. Okay, in other words, the whole distance, 14 plus 7, the whole distance is 21. If I cut that into thirds, I get 7. The shorter piece is 1/3 or 7. The longer portion is double that. It's 14. It's 2/3 of that. 2/3 would be twice of what 1/3 is. And then lastly, it says if PK is 39, so this whole distance is 39. If I divide that by 3, I get 13. That means the shorter piece here is 13, and the longer piece would be double that, or 26. That's how a centroid works. So it says down here, we're going to find the links. Given that CF, so from C to F, that thing is 27. And from A to B is 40. So this whole distance from A down to B is 40. Can we figure out the rest of the pieces? So can we figure out what G to E is? Here's G to E. Well, I know that from E to B is 22. That's the longer piece. So how do I go to the shorter piece? This was 2/3. So 1/3 would be, just cut that in half. So that's going to be 11. Distance from A to D. A to D. Okay, the distance all the way across. Well, if this from E to D is 12, then the distance from A to E has to be 24. If this is 1/3, the smaller portion is 1/3. I double it to get the 2/3. So from A to D all the way down, I'd be adding those two together and getting 36. From F to E, well, I know that the whole thing from C to F was 27. So 27 divided by 3 equals 9. So F to E has to be 9. And that means C to E. If this smaller segment is 9, to get the 2/3 part, I'm going to double it. This would be 18. All together, if I added 9 plus 18, I get the 27. The distance from A to C, okay, if you're going to go all the way across here from A to C, well, if this is 17, has 3 tick marks, over here with 3 tick marks has got to be 17. So the distance all the way down, you're going to add 17 plus 17. That's 34. And BF, okay, if this whole distance from A all the way down to B is 40, then each one of these has to be 20. Okay, they both have 2 tick marks, so they're both the same. So B to F is 20. And then C to D, that would just be this part, has 1 tick mark from C to D. Over here from B to D has 1 tick mark, and it's 15. So they both have to be the same. Okay, so you're going to be getting some pictures like this where you get to fill in the missing values. Okay, and then the last thing that we're going to go over, okay, it says on the coordinate plane. Okay, if you're working on a graph where your corners of your triangle have ordered pairs, okay, so I've got corners of my triangle where I have the ordered pair for each endpoint there, each vertex. It says the centroid is the mean of the vertices. Well, how do we find a mean? A mean is an average. So you're going to average the x values and you're going to average the y values. Okay, remember in an ordered pair we have x's first. So I'm going to take -4. I'm going to add it to 0. I'm going to add it to 3. So I just took all of the x values from each corner of the triangle. Okay, there's 3 vertices, 3 corners, so I'm going to take 3 x values. I'm going to add them up and divide by 3. To find the average, we add them up and divide by how many numbers there are. Well, there's 3 numbers. So I'm going to add those up. -4 plus 0 plus 3 is a -1 over 3. So that's my average x value. And then I'm going to do the same thing with my y's. So now I'm going to take the y value of each one of those, and I'm going to add those up. So that's going to be a 2 plus a 5 plus a -1, and I'm going to divide it by 3. Always dividing by 3 because there's 3 values. Okay, when I add these together, that's 7 plus a -1, that would be 6 over 3, and that's 2. So my centroid is, my centroid, where those medians are going to meet in the middle, is going to be located at -1/3, +2. If I go over a -1/3 and I go up to, it's approximately right there, which looks like a pretty good middle point for me. Okay, I think that's pretty accurate. But when you're given the graph and you have the ordered pairs to work with, you average the x values and then you average the y values, and your answer is an ordered pair. Okay, give that worksheet. There's actually a couple worksheets there. Go ahead and give them a shot.